Hi, this is Group DL, and this is our data science programming project. Our project is on crowd counting using deep learning. So, in a nutshell, our project takes input as an image and outputs the the count of crowd inside that image. So let's talk about the business value of a project. There's a lot of business value for this project. In the current scenario of social distancing, many governments are trying it hard to implement their social distancing protocols. Um, there are protocols where some states have that not more than 10 people can be in a crowd, some have 15, some have 20. So if such a technique like crowd counting can be used, it would be easy for the governments to be alerted about unusual crowds getting gathered up in some places, and they can stop such events from happening using such a deep learning based model. Um, there are many more applications of this. You can use it to record attendance of a restaurant to inform them about their um, popularity. We can use it in high traffic roads and public spaces. We can use it for counting the attendance in educational institutes, urban planning, video surveillance. One of the most famous examples of this crowd counting in action was seen in 2016 by the Indian government. So Indian government had implemented this in their Kumbh Mela disaster management. Kumbh Mela is an event in India where more than millions of people come to the Kumbh Mela uh, uh, for a religious event, and um, there are cases of stampedes many times in this event. So Indian government used this crowd counting and to figure out unusual crowd gatherings, and that helped them to implement disaster management protocols which could stop these unusual stampedes getting happening from crowd generation. uh, Now let's talk about the project itself. So the biggest problem that we faced to implement this project was that we had many images of crowd, but but there was no way that we had a data set which mapped our crowds to their actual count, so that we could use those counts as uh, our ground truth or our y true values. So we had to figure out a way to generate these ground truth values ourselves. So the technique we used to do that was density mapping. So basically, we took the density maps of a crowd images, and we applied the k nearest neighbor techniques on that to get an almost accurate ground truth value of the count of crowd in our images. Um, so we could use those density maps and those counts as the inputs for our model training. uh, because of this, we can now take any image on the internet of crowd, and we can gather the actual count from that image, and we could use that to train our model. So let's talk about the model itself. We knew that in order to accurately count an image, it was of the utter importance that we could perfectly extract the features of an image. The better the features of an image are extracted, the better a separation of heads can be achieved, and the better count can be in result generated. So, so that's why for better feature extraction, we used CNN models, and one model that stood out was VGG16. This model was originated in 2014 in an ImageNet competition, and this model is known to easily extract deep features of an image. So we used a modified version of VGG16, which is known as CSRNet, and CSRNet was specially built for to deal with images with high congestion. Uh, so the first 10 layers of this model are same as our VGG16 model, but the last 7 layers deal with handling the features and generating the density map. This model also ensures the auto encoding features because the output as a density map which is outputted from the model has exactly the same scale and size as our input image, which makes it easier to compare with our input image. I can show you this the sample of the project running. So you can see this was our image, and this was the output generated from our model of the image. You can see many of the distinguishable features of this above image. And if you see the count that is generated by the model, I mean the original count was around 13, and our model predicted around 9, which is I mean this is one of the case uh, where the accuracy was quite good. Uh, our overall accuracy of this project is around 27%, and there are reasons for it. It takes it takes a huge amount of time to train the model, and and also a lot of processing power. So we have right now trained the model for around 700 images, which has taken us a substantial amount of time, around 12 to 15 hours. So we are planning to gather more images from the internet, and we are planning to train the model furthermore to improve our accuracy in future. Our goal in future scope are also that we will try to implement this crowd counting algorithm in the realms of video, so that it can come very closer to our end goal of trying to make a project which could be also implemented in CCTV systems. Uh, our model is right now performing better on sparse crowds than the dense crowds, but I think more training will just make it much better. So basically our model is now successful in uh, finding out the crowd counts with a great accuracy in some of the examples. This was our project, and this was a great learning experience for us, because in such a small time of around 3 months we could work on this nice CNN based project, and we learned a lot about image processing. We learned a lot about density mapping, KNNs, VGG models, and something that would have been really hard if we didn't have the deadline in front of us. So I would like to thank you for the opportunity to work on this project, and hope you like this project. Thank you.